Thank you, class. All right, good. So today we are very happy to have Xiao from our own university coming. So Xiao is in the database group, just a snatcher. She's doing lots of algorithmic work. So the snatcher also to tell us a bit about her algorithmic work on query processing, etc. Yeah, I guess let you start. She's around. She's local. If anyone wanted to ask, like, talk afterwards. All right, go ahead.
Yeah. Okay, thank you for the introduction. So hello, everyone. My name is Xiao. Today, I'm very happy to be here and share some recent developments in join-aggregate query processing. I know the term join-aggregate may sound very specific to a database system, but actually it's a very general class of queries that can capture many commonly studied algorithmic problems as special cases. So this is a very vibrant research topic since we continue to deal with more and more complex data queries across different domains. So this requires us to have a better understanding of the algorithmic capabilities and the limitations. I hope this talk can be a starting point for collecting database algorithms and algorithms, since we share many interest in many common problems, but we just talked about them in different terminologies. Okay. So this is the outline of my talk today. I will start with a brief overview of join-aggregate queries, explain what they are and how they capture many analytical queries. Then I will review the previous results and then give a brief summary of our new results. The details of our new result can be found in these two papers. So the first one, fast matrix multiplication for query processing, appeared in PAS 2024. And the other one, output optimal algorithm for acyclic join aggregate queries, is under revision PAS 2025, also appeared on arXiv. Okay, then I will walk you through with two examples to illustrate the high-level ideas behind our general algorithms. At last, I will describe some interesting open problems with exciting opportunities for future research. Okay, let's start. I know many of you are experts on graph algorithms. So given such a social network graph, we can ask many analytical queries. For example, how many triangles in the graph? How many cycles in the graph, how many clicks in the graph, or a slightly more challenging question, how to list all those triangles, cycles, clicks, or any subgraph pattern you are interested from the graph. So all those questions can be expressed by the join-aggregate queries. Okay, let me use this example of listing triangle to show you how we talk about the triangle thing in database language. So in database, we store the data in structured tables or relations. And so the tables have multiple columns, which are called attributes. And each row in this table is a data record, okay, or a tuple, okay, in our terminology. And here to capture the triangle listing problem, we use the tables to store the edge information in this graph. So every row here is a tuple indicating an edge with two endpoints in this graph. And to find all the triangles in the graph, we have three identical copies of the edge relation, but we just rename the attributes of the tables into AB, BC, and CA. If we join these three tables, okay, their join result exactly returns all the triangles in the graph. So for example, the tuple Alice Bob will join Bob David because they share the same value Bob on attribute B, and Bob David will join with David Alice on the attribute C, and again Alice Bob will join with David Alice on attribute A. Okay, so these three tuples will form a join result, and which finds the triangle Alice, Bob, and David in this graph.
Sorry, question about this. I noticed that like E1, E2, and E3 are all the exact same in terms of like the entries. Did they have to be, like, for example, if the first one had Alice Bob, the second one had Bob David, and the third one had David Alice, would that be sufficient or not?
Yes, it's a self-join. So it's join itself, so all the relations should be the same. It's also the, okay, yeah, it should be the same.
Okay,
So, okay, so the join, sorry.
It's irrelevant that your three tables are the same.
It's not relevant or it's relevant? I think it's.
It- I mean, I see what the question is and what the problem is and what the answer is. Another question is, you ask such a question, you start out by, what your mind is, how many triangles are there?
Yeah.
Which, are you gonna get into the distinction between how many and listing?
Yes.
Good, fine.
It's a
Right,
counting part, yeah, so this is the listing part, yeah, okay. So actually, yeah, if we only use the join operator, we can only do the listing and enumeration problem. And you can see the, sorry, the join is exactly the pattern matching problem from the query graph or query hypergraph to this instance graph, okay. Okay, yeah. So actually you can ask more complete questions on graph. For example, can you find the shortest path? Can you find the maximum reliability between two nodes in the graph? So all those things can be captured by the join-aggregate queries, and the tables just store the edge relation information in the graph. And also you can ask the colorability, which is an example of the constraint satisfiability problem on graph. So you can have the conjunction and disjunction to encode those constraints. And for every constraint or every clause, you have a table to store the truth assignment. Okay, so that's how you do the join things. Okay. Next, let me give you another example in a different scenario. So which is the matrix multiplication. Okay. In database terminology, we will translate each matrix into a table of two attributes. So the first attribute will encode the row ID of the matrix, and the second attribute will encode the column ID of the matrix. Okay. So every non-zero entry in the matrix will be stored as a tuple, with the first value indicates the row ID and the second value indicates the column ID. And we can see that the table R3 is exactly the projection of R1 join R2, and then projecting away the middle join attribute.
So projection is sum of those.
No sum of, it's just a remove duplicate. Okay, I can give you an example. Yes. So if you look at this entry in the output matrix, and it corresponds to this table in the output table. So it's the inner product of these two vectors, but it's also the join result of 2, 1, join 1, 1, and then project onto AC, which is 2 and 1. Does this make sense?
No, I'm trying to get what project.
Sorry.
What is the projection of the loop?
Oh, the projection is that after you join R1 and R2, you will get a table with 3 columns, A, B, C, right? And you just look at A and C.
But what do you do if then you have multiple entries that are the same for A and C? Do you
Exactly.
sum them?
We do not sum. So for the Boolean version, we just do the union.
see entry 2, for example,
Yes.
where it would be like 2, but we just cap it at 1, I guess, right?
Yes, this is a true and false.
This is
This is not regular matrix.
This is the Boolean matrix multiplication.
Got it.
But you could also do the number multiplication, if you want to really make multiplication fast, you would go through the number multiplication anyway.
Yeah, later I have an example to show if you want to go to like integer and all those things. Okay, so after these examples, I hope you are slightly convinced that join-aggregate queries are a very general class of queries that can capture many commonly studied problems. So next, I will introduce the formal definition of join-aggregate queries. First, it's the join query. So a join query could have multiple tables of relations. Okay, R1, R2, to Rk in this formula, and each of them is defined on a subset of attributes, okay, which I define as E1, E2 until EK. So the join query is essentially consider all combinations of tuples, each from one relation, such that they share the same value on their comp attribute. Okay, so in other words, if you consider the join result of Q, this is exactly all the tuples in the domain of attributes, okay, such that the projection of this tuple on every subset of attributes is a valid tuple in the equity tables. Okay. And even just use the join operator, we can express many analytical queries on graph. For example, if we want to list all the triangles, we can have three relations: AB join BC join AC. And if we want to find less key packs or chains, we have key relations with attribute A1 join A2, A1 A2 join A2 A3. Okay, so on and so forth until we join AK and AK plus 1. Okay.
Sorry, just notation wise, in the join, it's always assumed that there's a unique attribute that's shared. Like which one do you combine on, or is that always clear from context?
So it's actually, so this is for the graph pairs, you just say, okay, any pair of relations just share one attribute. But
I'm just looking at that first one with the triangles. If I join E1 and E2, then I get things that have A, B, C on them. And now I join with A3 that has AC. So do I join on both AC or only on A or only on?
pairs, every pair of relations should join.
I'm trying to see that.
So E1 and E2 will join attribute B, E2, E3 will join attribute C. And then E1, E3 will join attribute A.
Maybe it's not that, but I'm not
Okay.
following how you do this.
Just think of it as a three-layer graph. You're counting the path, but you're looking at the paths that go and share a vertex in a middle.
I should clarify, I understand entirely why this is kind of working. What I'm asking is what the join operator exactly expresses, in what parentheses order are you evaluating this, that kind of thing is what I'm asking.
Because the join operator is commutative, so you can do any ordering, pairwise ordering. Okay, so yeah, you can also, yes, find like the stars in the graph or the cycles in the graph. Okay. Next, to define the join-aggregate pairs, we need a mathematical abstraction from algebra, which is the commutative semirings. Okay, so commutative semiring consists of 5 elements. So the first one is the domain of the elements. Then we have another 2 binary commutative operators, summation and multiplication. And we also have 2 identity elements. So there are several conditions implied by the definition. So the first one, the domain D and the summation and 0 forms a commutative monoid with identity element 0. So there are 3 operations follows the definition. And also the domain of D multiplication 1 forms a commutative monoid. Similar thing. And also this multiplication operator distributes over this summation operator. And also for any element in this domain, if we apply the multiplication of this one and 0, we will also get 0. And a commutative semiring can be a ring if some additional condition is satisfied. So we said that for any element in this domain, we can always find the additive inverse. Okay. So this is very important if we want to apply fast matrix multiplication techniques, because we need the operation of the inverse operation of addition. So this is also the reason why we couldn't apply fast matrix multiplication techniques for general commutative semirings, because some semirings does not have this inverse operation. Okay. Some examples, okay, of the commutative semirings, like the Boolean semiring. So if we have the the true false and also the disjunction and conjunction operator and then true and false as the identity element, we can express the conjunctive query or the join projective query. For example, if you want to detect whether there exists a triangle in the graph, we can use the Boolean semiring. Or we can also have the mean sum semirings to capture the shortest path. For example, you have the this sum to calculate the total distance of one path, and then use the min operator to select the minimum path. And also we can have the integer sum product ring so that we can encode the integer matrix multiplication. Okay, now we are ready to define join-aggregate. I promise this is the last slide with so many notations. Okay, so the join-aggregate query is essentially the aggregation over the underlying natural join queries. So we will, so for the join-aggregate query, we will split the attributes into output attributes y and the aggregate attributes bar one. Okay. And we call a join-aggregate query is a full join if all the attributes are output attributes. Okay. And to encode the aggregate function, so now each tuple is enriched with the width, okay, which is a semiring element from this domain. And the annotation of a join result is defined as the multiplication of the annotations of the corresponding input tuples participated in this join. Okay, now the join-aggregate query will just first compute the join result as well as their annotations. Then it will partition the join results by the output attributes into groups. And within each group, we will apply this summation operator to sum their annotations. So the query result of a join-aggregate query is a set of pairs. Okay, so the first element is a result in the projection of the full join result, and this is the annotation of this query result, so which is the summation of all the full join results that share the exactly same value, output attribute value with the t query. Let me use, yes, the integer matrix multiplication to illustrate this process. So now we enrich each tuple with another column, which is the weight of the tuples, which is exactly the value in the matrix. Okay, and if you consider the annotation for each join result, which is exactly the multiplication of the weight of the corresponding tuples, and if you consider annotation of this query result, so we just find all full join results with the same 2 and 2 attribute A and C, and then sum their annotations. Okay, this is clear. Okay.
I guess I find this example is clear, but the overall like framing a little bit to a lot of
Yeah.
but at least would it be sufficient to think about it in this example, or do you think that it would be useful to think about it more generally as well?
I think so far you can just interpret this as a sum product, but I just want to emphasize that there are so many different, commutative semirings, so you can do, different things,
Yeah, it's just from most of our points of view, I think we're trying to translate from matrix operations to something in databases.
Okay. Great. Okay, so if we have more than 2 tables, so we can a generalization of the matrix multiplication is the terminate. So now we have a chain, but we are only interested in the hat and the tail attributes, so A1 and A2 plus 1, and we just aggregate over all the middle attributes, A2, A3, and A4. Okay, to study the join-aggregate problems, we actually have 2 inputs. So one input is the data, is the database for the graph. And the other part is the query, is the pattern we are interested in. And to study this problem, we are interested in the data complexity. Okay, and we assume the query size, which is the number of attributes or number of relations as a constant. And we only use data-dependent quantities, such as input size and output size as a complexity measurement. What does this mean? Okay, so for the graph, the input size is the number of edges, and the output size heavily depends on the aggregate function you are interested in. For example, if the query is the counting query, we just output a single count value. If this is the detection query, you will output a single Boolean value. And if it is a triangle listing query, you will have a list of triangles and the output size could be polynomially large in terms of the input size. Okay. And for the matrix multiplication problem, the input size and output size are exactly the number of non-zero entries in the matrix. So we actually study matrix multiplication problem in a sparse setting. Okay, next I will give you some overview of the previous results. So in the literature, we have investigated different structure properties of the query graph or query hypergraph to measure the hardness of the problem. Important notion is the acyclicity of the query hypergraph. There's a quite a simple way to decide whether a query is acyclic or cyclic in graph. So if it does not have a cycle, it's acyclic. If it has a cycle, it's cyclic. But for hypergraphs, the condition is much more complicated. I won't go into the details, but I hope it's clear enough for just for graph queries.
So Michelle, all the
Yeah.
examples you showed us were queries of graphs, no hypergraphs dropped off three relations.
Yes, exactly. Because every relation or every edge is a hyper edge, so it could be a subset of the edges.
And is it look like tensor multiplication where you have three?
Yeah, you can have three things. Yeah, you can have arbitrary hyper edges.
Right.
Yeah. And as early as 1981, Yannakakis proposed a very famous algorithm that can compute all the acyclic full join queries in linear time, proportional to the input and output size. So in the acyclic join query, all the attributes are output attributes. For example, if you want to find all the trees in a graph, that's an example of acyclic join. And the same time complexity can be slightly extended to free-class queries when the query is not full. So you can allow some aggregate attributes. I won't go into the definition of free-class. And this one is just to measure how the output attributes are clustered in a query. So this is a very strong condition, and many queries are not free-class. For example, the matrix multiplication queries. So for the large remaining class of acyclic but non-free class queries, yes, there's no hope for a linear algorithm, and there's some well-known conjectures. And for the matrix multiplication query, people give a tighter analysis and show that all the matrix instances can be computed within n times root out time.
What does it mean for acyclic queries? So for example, if I'm given an undirect graph, does it enumerate all spanning trees of the graph?
So the acyclicity is defined on the pattern. It's on the query hypergraph. It's not on the database. It's not on the graph, instance graph you mentioned. So for example, the triangle is cyclic. The path is acyclic.
So I'm giving a specific pattern to you, which is acyclic.
Yes, you can decide.
Oh, okay.
Yeah.
So like, are these results for subgraph listing or is it some more general problem? Like I'm a little confused.
You mean the acyclicity?
No, like all of these, like what's the problem which is being solved here? Is it like you're given a subgraph and you want to list all the subgraphs, or is it like more general?
Okay, so when I put queries, I meant all the join aggregate queries. But when I meant the join queries, so this is the listing problem. You want all the attributes to be the output attributes. Okay, now, for example, the matrix multiplication query is not a join query because you aggregate over some join attributes and you are only interested in a subset of attributes.
So are you saying matrix multiplication, square root of the number of outputs? I'm reading this wrong, because I'm reading it saying matrix multiplication, square, a number of outputs is most n square, let's suppose there are n inputs and n is the size of the matrix, order n. So you could and the outputs are most n squared.
Yeah.
So if you've got an n, order n input graph, graph with order n edges, you can do a product in quadratic time.
I think that n squared though,
Yes.
because like that n is like the number of entries, which would be like the side length squared, right?
No, n, yes, no,
So I think
no,
total.
no, I'm just having an n by n matrix with order n
Oh.
edges in it. That's where I was going.
A sparse matrix.
Yeah.
So you become order n time, no? If you have n
Yeah.
edges, this is m n, you should handle matrix multiplication, m n time.
Yeah.
So the sparsity of the matrix, okay. And as a generalization of the matrix query, we have the star queries. Still have the star queries, like all the key relations joining on the middle attributes, but we are interested in the boundary attributes. So it's a generalization of the matrix query when k equals to 2. And for the star queries, this analysis can be generalized to n times output. So this is related to the number of relations in the query. So both results are already output optimal. However, for example, for the chain queries and all other queries, only an upper bound in the last 40 years. Okay. So that's the current state-of-art result for the Yannakakis algorithm. People are also interested in what's the best we can do when the output size is as large as the worst case. I would like to share this result because it's very beautiful and elegant, which is, I think, is the biggest breakthrough in database theory in the last 10 years. So it's also related to the information theory. It says that for any arbitrary join queries or the enumeration problem, this algorithm can solve the enumeration problem within time n to the power of row star time. So row star is a very interesting query-dependent quantities, which is the optimal fractional edge covering number of the query. Okay. Let me do a quick quiz. So can you guess what is the row star for the triangle? Yeah, great. So actually, this number will assign weights to the edges such that every vertex is covered by some total sum of weights in at least one. So for the triangle, we can assign 0.5, 0.5, and 0.5 to every edge, and every vertex is covered. Okay, so so this also explains, okay, in your graph, there are at the most n to the power 1.5 triangles in the graph. Okay. How about for the cliff? Almost there. K over 2. Yeah. You just assign k, yeah, 1 over k minus 1 to every edge. Yeah, okay. And for the cycle is, yeah, it's more obvious. It's k over 2. And so, okay, this is the hypergraph beyond the graph queries, which is the Loomis weighted join. So the Loomis weighted join will contain key relations. So each relation contains all attributes except one. Okay. And for this one, okay, we have the row star as a k over k minus 1. Okay. So this line of algorithms focus on the worst case, so their complexity is only in terms of the input size. Okay, it does not depend on the output size.
So who are the authors?
Okay, so the authors, I think the first capital N is the NGO, Ham NGO, who is a professor from U Buffalo. Now is the research scientist in relational AI. And Arturo, I think one R is Arturo from who worked on the coding and and Christopher Reeves, some professor from Stanford University. So I can share with you the information. Yeah. Okay. So as a brief summary, previous result has achieved 2 flavors of running time. Worst case optimal algorithm are good, but worst case rarely happens in practice, and they are only known for full join queries. output optimal algorithms are great, but they are much more difficult to design, and we only have very limited understanding of output optimal algorithm. And okay, this has been left as a big open question in database theory. How can we find a better way to evaluate acyclic queries? Okay, currently we only know the Yannakakis algorithm. And an interesting implication of this improvement will be that all the cyclic queries can automatically benefit from those results if we use the tree decomposition techniques. Okay, so yeah, in short, all those things boil down to a question: can we have the output optimal algorithm for cyclic join-aggregate queries? Okay. Next, I will use 4 questions to give an overview of our new results. So the first question is whether we really need a new algorithm to do that. Okay. In other words, is the unsatisfactory upper bound n times out due to the fundamental limitation of the Yannakakis algorithm, or just because we don't have a type analysis? So in this paper, we first showed that this bound is already typed for the chain matrix multiplication queries, in the sense that we found some database instances on which this Yannakakis algorithm indeed requires n times out time. And this condition has been generalized to non-hierarchical queries. Okay. So the next question is, what's the lower bound? Since we are targeting optimal algorithm, then what's the target of output optimal algorithm? What's the lower bound for computing acyclic join-aggregate queries? We first showed that for the chain queries, we need at least n times root out time. So this has exactly the formula with the matrix multiplication queries. And moreover, for the general acyclic queries, we show this formula. And this lower bound is related to a new notion of the width of the query graph, which is the free convex hypertree width of the query. So briefly, intuitively, this width measures how far a general query is away from being free convex. Okay. So for the chain queries, this width is 2. Now you can see that, yes.
So n rules out, just are you programming for every choice of n and every choice of l?
Exactly, this parameterized.
Sorry, question here about like, is this a lower bound versus a combinatorial algorithms? Are you like discounting like algebraic algorithms or something? Okay, I see. Oh.
So now
Requires some combinatorial matrix multiplication.
we don't allow any fast matrix.
Right, is that sort of an equivalent way to think about combinatorial algorithms? Like,
So what is the hypothesis?
You're not allowed to do numerics.
For the lower bound?
I think the combinatorial is a little bit weak here because people don't have a very formal definition of the combinatorial. Here we have to consider. We don't allow fast matrix application, and all those semiring elements should always be computed by applying these 2 operators. So we would not allow any leading operators. So that's our assumption.
So do you have a hardness assumption, or is your hardness assumption that Boolean matrix multiplication cannot be done in cube time, or you have a stronger hardness assumption?
Our assumption is that since we have a commutative semiring, so all the semirings can only be obtained, new semiring elements should always be obtained by applying the summation or the multiplication operators on existing semiring elements.
I see.
so it's like basically every algorithm that can be done with a specific set of queries, or sorry, not queries in that, but specific set of operations. That's
Yes.
okay.
Yes. So you can see the gap between the existing upper bound by the Yannakakis algorithm and also the lower bound. So this motivates us to find the new algorithms, okay, for acyclic queries. And actually we found a matching upper bound, okay, for general acyclic queries with the exact formula in terms of the free convex hypertree width. This result has unified all the previous upper bounds. For example, this width is 1 for three connected queries. So we recover the n plus out time result. And this is width is key for star queries key relations. And this width is 2 for chain queries, no matter how many relations are in the chain. Okay. Okay, last exciting question is beyond the combinatorial algorithm, can we do better for acyclic join-aggregate queries? Yes, if we use fast matrix multiplication for rings, for example, the join project queries, we can do better. So the first result has been confirmed, proposed in the SODA 2024 paper, which is fully sparse matrix multiplication. It has improved the results from n times root out to n times out powerful 1/3. Okay, and we also extend this result for general acyclic queries. So you can see the polynomial improvement on this exponent for the output size. Okay, so that's the overview of our new results. Yes, you are right. Yes, for simplicity, I assume omega is 2. Otherwise, the formula is very messy and complicated. Yeah.
So it's actually a little bit worse than that based on whatever omega actually is, right? Or
if omega is larger than 2, I think this one will be larger, but when omega is 3,
Yeah.
we will just degenerate to this one.
I see. But we know omega is going to be less than 3, so okay, cool, gotcha.
Yeah. Okay, I will use the remaining time to show 2 examples of our new algorithm. But I hope to emphasize the two-way street between the database queries and the matrix multiplication. So in the first example, we will show how the classic algorithm for database queries can speed up chain matrix multiplication. And in the second example, I will show how the recent development for matrix multiplication can speed up database queries. So let's enter into the first one. Okay, before we enter into the new algorithm, let's start with some questions. The limitation of the Yannakakis algorithm on this line 3 chain queries. On the chain queries, the Yannakakis algorithm essentially degenerates to the parentheses algorithm. So where we should put the parentheses to compute which 2 matrices first. On this example, we can put the parentheses on the first and the second matrix, which corresponds to a current plan database. Okay. We do the join R1 join R2 first, and then we aggregate over the join aggregate A2, and then we do the join with R3. Okay. Or we can put the parentheses on the second and third matrix. So this corresponds to another current plan. So we can do R2 join R3 first to aggregation, and then join R1. My question is, which current plan is better? You guess? A little bit hard to say. Okay, let me show some instances here. So this is a 4-layer graph, and all the edges are the tuples in the tables, and those numbers are the number of values in this layer. Okay. On this instance, if we apply the first plan, which is we join R1, R2 first, we'll materialize n times out intermediate result. Okay, if we do the join first. But the second plan will be much more efficient since you can see the domain here is very small. So it will only generate n intermediate result. Does this mean the second plan is better than the first one? Good. Yeah. If we have a symmetric database, these 2 current plans will just have opposite behaviors. Now the first plan is much more efficient. Okay, then my question is, for any instance here, can you always find a good plan? Unfortunately, the answer is no. If I just put these 2 instances together, so both query plans have to materialize n times out of the result. So this bad example rules out the possibility of a globally good plan for database. But it precisely points us to the right direction. If we could decompose the instance into multiple pieces, then it's possible to find a good plan for each piece. Okay, so that's the idea of the hybrid strategy. And
So what does Yannakakis algorithm do on the database that have both of these?
so the Yannakakis. So the Yannakakis will just have these two plans. So it will just pick one plan and apply to the database.
But then if you get something that is more than n plus out.
What do you mean by n out?
Oh, yeah, okay. I thought Yannakakis algorithm gets n plus out on.
Only for free connected queries.
I see.
But this is not free connects anymore. So all the matrix multiplication queries are not free connects. So that's why we want to, study this problem. So the general question is, okay, what to partition? So it could be possible to partition the input relations or even the intermediate query results, and then how to partition using which degree threshold. And at last, after we are done with the partition, which query plan to pick for each sub instance. Okay. Okay, so far I just assume a constant approximation of the output size is known. And this can be can be obtained using different techniques. If you are interested, I can talk more in details. Okay. Now for the chain queries, there are so many different plans. Even for the 1K equals to 3, there are 2 plans, but for general K, we have multiple different ways to put the parentheses. But we actually using 2 query plans. Okay. The first one is that we have a very nice state on the right-hand side. So we will compute RK-1, join RK, and then do the aggregation, and then with RK-2, okay, so on and so forth, until we join with the leftmost relation R1, and then we do the aggregation. Okay, so this is the first candidate plan we will consider. The second.
Are you really saying that? I'm not sure if all of you.
Yes.
But what I'm getting, when you're doing these things, if you get something where fast computation is gonna be a win, you do it there, and if it's not, you don't.
You mean fast matrix multiplication?
Yeah.
Yeah, so far we haven't talked about fast matrix multiplication.
Oh, that's what I'm looking at. Where it's dense, you're gonna do that.
Yeah.
And where it's not, you're not.
You already get the idea of my second example. Okay, yeah. Yeah, so another query plan is that we have nested parentheses on the left-hand side. So we will do this join-aggregate process from left to the right. Okay. Okay, then I think the challenging question is how and what to partition.
If I just set the number of non-zero entries, so like approximate that for every multiplication, does that give you a bound on the cost of like if I give you parentheses and I tell you these are the number of non-zero entries you get in their multiplication, does it estimate the cost, the final cost that you have?
But it's the worst case.
In the worst case on this.
In worst case, in terms of n and out. Or just in terms of n.
No, in terms of the actual value that they have, like I tell you, if you multiply this and this and this, you're going to have like 1,000 non-zero entries.
Yes, yes.
And if you have all those numbers,
You can have better, more fine-grained accuracy, fine-grained complexity formula in terms of the intermediate
got
results.
but those numbers you can get with the sketching also, not if you multiply with the low dimensional matrix.
Yeah, I think you can have better algorithm if you have more information on the like the intermediate results or the accurate information. So far, we just use 2 parameters n and out. So I think this is how to do partition is the most technical part of the algorithm. So we first partition attribute A2. Okay, so a value in attribute A2 is heavy. It appears in more than tau tuples in R1. So tau is the parameter which will be determined later. Then we can partition the R1 into R1 heavy and R1 light based on the attribute A2. Then we continue the partition. But now we change the partition criteria slightly. So now a value in A3 is heavy, it appears in more than 12 tuples. Now in a subquery, which is the join between the line tuples in R1 and the table R2, and then we aggregate over A2. Okay. And similarly, we can get R2 heavy and R2 light. We do this partition, yeah, so on and so forth until we are done with the partition AK. And now in the last part, we get everything is light, so it is subquery. So actually, in this partition process, we will decompose the original input database into K sub instances. So for the first K-1 sub instances, we always have something heavy. Okay, like A2 is heavy, A3 is heavy, A4 is heavy, something like that. And except for the last subquery, sub instances, everything is light. Okay. Next question is which query plan to choose. Okay, in the first case, if any attribute is heavy, we just choose this query plan from right hand side to left hand side. And if all the attributes are light, we choose the other plan, okay, from left hand side to right hand side. Okay, now we just analyze the cost of this query plans. In the first case, if any attribute is heavy, which means that it can be joined with at least 12 tuples in A1. Okay, now if we consider the active values in the tail attribute AK plus 1, it will join with some heavy value in AI, and then join with at least 12 tuples, 12 values in A1. So each active value in AK plus 1 will appear in at least 12 tuples in the final output, and they are at most out of final output. So the number of such active values can be bounded by out of it. Then if you just look at the join aggregation process, you can say that the intermediate result is always bounded by some relation and the active domains of the active values in AK plus 1. So this can be bounded by n times automaton. And in the remaining case, if everything is light, means that okay, everyone can join with smaller than 12 values in K1. And if you just look at the intermediate result materialized, we can always split into like the relation Ri and also the degree of every value in AI light to A1. So this can be bounded by n times tau. So our final thing is to find a good parameter tau to balance these two terms. Okay, so we can set the value of tau as we root out and then achieve such a complex.
You're multiplying matrices. And you're looking at associating from the left or from the right, why not arbitrary, or are you gonna get to that?
Arbitrary.
Then do the middle ones first, whatever works.
No, I don't think.
It all smacks of pop, and curve, box, whatever it's called, 69 or 70, curiously immoderate.
I guess he's asking why didn't we go left to right or right to left?
Yeah.
It'd be a better strategy where you do a middle multiplication and then do the one to the left of it and something like
Yeah,
that.
and whatever works. If you, to the extent you can figure that out, which,
I think maybe from the analysis part, for example, if we can always, sorry. Let's look at one, everything that happens, we just want to be sure that AP plus 1 is very small. So in a very beginning example, when AP plus 1 just have one value, we need to know that we need to carry this AP plus 1 to the matrix multiplication from right hand side to left hand side. I would say these two calculations are enough to help us get such a result, but the question is, if we have other calculations, can we do better?
if somebody said, you run into this problem with lower bounds, because magically, you should choose some magic order,
Yes, but
which has the problem of what larger things are created and when it makes sense to use fast multiplication, when it makes sense not to. So I understand there are complications. But it does remind one of having a sequence of matrices to multiply, not this thing. And in what order should one do it? And that was the work from a long time ago that I was referring to.
That might be a good pointer for us to study fast matrix multiplication for chain queries. So far, if we just focus on combinatorial algorithm, I think these two plans are already enough, but we don't have any fast matrix multiplication algorithm for chain queries. So yeah, that would be a good starting point.
In combinatorial algorithm, these are worst case optimal in terms of n, but they're not instance.
Yeah, that much yes. Okay, so now we will go to the second example using fast matrix multiplication to speed up the star queries. Similar thing, we want to figure out what's the limitation of the existing combinatorial algorithm. So on these 3 star queries, so if we have the A1, A2, A3, each attribute, the domain of each attribute is as large as out to power 1/3, and the middle attribute has n over out to power 1/3 values. And every relation is just a Cartesian product. And the argument is that all the query plans have to materialize all the join results. So no matter which 2 relations you decide to join first, you cannot drop the middle join attribute, right? Because it's some information to join with the third relation. So the only thing you can do is just materialize all the full join results and then do the aggregation. However, if we bring fast matrix multiplication into the picture, we can do much better. For example, we can have the first matrix to encode the first relation, and the second matrix to encode the join result of R2 and R3. So this matrix has the row as actual B, and the column as the combination of A2 and A3. So their result will give us A2 and A1 and A2. So yes, for this high instance, if we use matrix multiplication, we can do much better than the combinatorial algorithm. So yeah, similar question here is what and how to partition, and which query plan to choose, because now we already have the Yannakakis algorithm and also the fast matrix multiplication algorithm. Okay. So for the star query, there's quite a simple way to partition. We just look at the degree of each value B in each relation. Okay, without loss of generality, we assume the degree is in a decreasing order. Otherwise, you just consider all the possible permutation of those degrees and apply the algorithm. Okay, and now we consider a value B is heavy if the delta 2B times delta 3B into delta QB is smaller than tau, and the light is greater than tau. Sorry for the typo. It's greater than tau, and the light otherwise. Okay. Okay. Then for the sparse part, which is when the values in attribute B is light, we just apply the Yannakakis algorithm, which is just to do the full join and then aggregation. And for the dense part, we do fast matrix multiplication. But the non-trivial thing is how should we form those matrices, since we only have 2 matrices? So how do you do the partition of the relation? The observation is that okay, if you have like an intermediate partition of the relations, so this column and this row are the heavy values of B. But for the first matrix, we have the A1, A3, A5. And for this column, we have A2, A4, A6. Okay. The reason is that we want to balance the dimension of these 2 matrices so that the cost is minimized. Because you can have an arbitrary partition of the output attribute.
Yeah,
Yeah, okay.
this is what I'm very important.
Okay, so the tricky part is how can we bound the cost of this fast matrix multiplication? The first observation is that we can bound the input size of this two big matrix by n times root out. Okay. And also we know there are at most n values in the heavy in the attribute B, so the middle dimension is at most n. And the good thing is that we can always bound the domain size of the first dimension and the third dimension by out over root out. So this is the a little bit complicated. I think I will just skip those details first and give you a high-level idea of the hybrid structure of these two paradigms. So for the dense part, for the sparse part, the cost of the Yannakakis algorithm can be bounded by n times tau. And for the dense part, the matrix multiplication can be bounded in this way, which is just related to the three dimensions. Okay, and that's how we set the value of tau to balance these two terms and get such a time complexity. Okay. Okay, so let me give a brief summary of all these existing results. So for the semiring algorithms, we already know what's the optimal way to compute acyclic join-aggregate queries. But for the beyond semiring or combinatorial algorithms, we only have output-centered result for star queries and acyclic queries. This is also unknown if we can use fast matrix multiplication to further speed up chain matrix multiplication. And we also don't know the optimality here. So I hope these examples can illustrate the power of hybrid strategies. We usually want to answer how to and what to partition and which query plan to choose. So in our full paper, you can find the more complicated strategies to do this partition and also to bound the cost of each query plan. Okay. So at the last, I want to share some interesting open problems in this area. So the first direct question we can ask is, what is an output optimal algorithm for computing cyclic join-aggregate queries? Okay, so there are some lower bound results in the literature using the click imbalance techniques. So their conjectures are based on the Boolean click or the mean weight click problems. But yeah, we don't have any non-trivial upper bound for cyclic queries. And also, can we have better fast matrix multiplication algorithm for acyclic queries, I know this problem has been studied for a while in the algorithm community for detecting clicks, cycles. And very recently, we have a general result, which is appears in our archive, is how to use fast matrix multiplication to detect arbitrary hypergraphs. Okay. And also, fast matrix multiplication can be used for listing triangles, cliques, and cycles. And very recently, I found that it can also be used for approximate counting and also in the dynamic query processing. Yeah. So all those questions are very interesting and fundamental. So from the data system group, so we also want to know how can we implement those algorithms with the recent development in GPUs and TPUs. Okay, so that's all the things I want to share. And, thank you for attending my talk today.